Welcome to the Newton online class. In this particular class, I want us to study a particular topic in physics, and that topic is elasticity. That is elastic properties of a solid under mechanics. Now, what do we mean by elasticity? Elasticity simply means the ability of a material to regain its original shape and size after the distorting force has been removed. Then, that will tell us what we mean by elastic material. By elastic material, we mean any material that can regain its original shape and size after the distorting force has been what? Removed. For instance, something like a rubber, like balloon, rubber band, spring. All these are elastic materials. For example, I have rubber band here. You can see this rubber now. It can stretch when force is applied. And when I remove the force, it can go to its original shape and size. So this rubber is thereby an elastic material. It's an elastic material. So that is it. Then there's a prominent law there based on experiment by Hooke's, and that is what we call Hooke's law of elasticity. Now, what do you mean by Hooke's law of elasticity? The Hooke's law states that provided that the elastic limit of an elastic material is not exceeded, that the extension is directly proportional to the applied force or the stretching force. That the law states that provided that the elastic limit of an elastic material is not exceeded, that the extension is directly proportional to the load or applied force. That is very simple. Like this material, if I apply small force, it will expand or extend small. If I apply more force, it stretch more. If I increase my force, it keep on stretching until it reaches the elastic limit. Now, that's what the Hooke's law is talking about. So from Hooke's law, we have that F is proportional to E. F is the applied force or load. Then E is the extension, which means by equation, have that F is equals to KE, where K is the elastic constant of the material, or the stiffness of the material, or the force constant of the material. That is it. So this is Hooke's law equation. Okay, now let us look at this graph. This is the graph of Hooke's law. That's the graph of load against extension. Now, from this graph, we notice that from here to this point is a straight line. Then, from here to this point, you see curves. So, let us interpret this graph. Now, this graph by implication means that the point P on this graph stands for proportionality limit. Proportionality limit. That is the point at which Hooke's law is obeyed. Which means from this point O to this point, Hooke's law is obeyed. That is straight line. That is proportionality, direct proportional. Which means the load is proportional to extension from this point to this point. Then, the point E on the graph is the elastic limit. The point E represents the elastic limit. And what do you mean by elastic limit of an elastic material? It is the point on the elastic material beyond which the material cannot regain its original shape and size again. So when you stretch a spring, for example, it will, as you apply force, it will be extending. There will be a point when you stretch it more, you overstress it, then it will no longer return to its original shape and size. Then by that time, it has exceeded its elastic limit. So that point, which beyond that point, the material cannot return again to its shape and size, is known as what? The elastic limit. Okay, then we have what we call the yield point. This Y represents the yield point. The Y here, yield point. From the word, the yield, that is succumbing, collapsing. So the yield point of an elastic material is the point on elastic material where the material yields its elasticity permanently and it becomes plastic. Because opposite of elastic is what? Plastic. So the yield point is the point on the elastic material. When you stretch an elastic wire or a spring, the point at which the material yields or surrenders or succumbs its elastic property permanently and becomes what? Plastic. That's the yield point. Okay, then we have the point OY, OE. From O to E here, we call it elastic region. From O to E, the material is still elastic. But the difference is that from O to P, Hooke's law is obeyed. Then beyond P, Hooke's law is no longer obeyed. Then the force is no longer proportional to the what? Extension. Then from O to E is the elastic region. Within that point, the material can go back to original shape and size. Then Then we have point EB. From E to B here, the point E to B is what we call the plastic region. Beyond this elastic point, every other point here is the material has become plastic. It has teeth. It cannot go back to original shape and size. Like when you get a spring and stretch it, there is a point it will stretch, cannot compress back. That is it. Then the point B here is the break point. This is the break point. That is the snapping point. When you overstrain that material, apply more force to it, what will happen is the material will snap or break. Like I have this rubber now. If I begin to strain this rubber to some extent now, I apply more force, it will snap or break. That is it. Then, so this is about this graph of Hooke's law. This describes the pattern or the behavior of an elastic material when force is being applied or load on it. Then, we now look at other similar terms we have here. Tensile strain, tensile stress, tensile strain, Young's modulus. Now, what do you mean by tensile stress or the stress of elastic material? Stress simply means the ratio of the force, that is stretching force, or the applied force, or the compressing force, to the what? Cross-sectional area of that elastic material. So, tensile stress is the ratio of the applied force, or the stretching force, to the cross-sectional area of an elastic material. By implication, stress equals force over area. Force over area. That is the unit of stress. Unit, where now the force is Newton, area is meter square. Newton per meter square. That's the unit. So that's tensile stress. Then strain. Then tensile strain is simply defined as the ratio of the extension to the original length. The ratio of the extension to the original length of the material. You should be mindful of this because when the material has initial length, as when it has initial length, like this, and we apply this, maybe this is a spring, it has initial length as L1, and we apply a force on it to stretch it further to this point. So from here to here now, you have L2. So from this point to this point is the extension. So that is it. This is the original length. So the stress is the ratio of original length to the what? Sorry, the ratio of the extension added to the what? Original length. That is it. So stress equals to, it will now be equals to the strain. The strain now will now be equals to extension over original length. Now you can call it L0 or L1, original length. That is it. It has no unit because extension is in meter and the length is in meter. It will have no unit. Then for the Young modulus of elastic material or Young modulus of elasticity simply implies the ratio of the tensile stress to the tensile strain. The ratio of the tensile stress to the tensile strain gives you the Young modulus of what? Elastic material. In other words, you can say that we can state Hooke's law in another way. That stress is proportional to strain, provided that what? Elastic limit is not exceeded. In such a statement, the Young modulus becomes the what? The constant of proportionality there. Like we have K here. So here we have that Young modulus is equals to stress over strain. So stress tells us about the distorting force. While strain describes the measure of deformation on that elastic material caused by the distorting force. Then we'll talk about work done. By this you can derive a formula from this now. We can say that, in other words, we can now have that our Young modulus can now be, it is stress over strain. By formula, we can now say that it is FA times, but this is E over L, that FA times L over what? E. So we can now say that our Young modulus is equal to FL over AE. And the unit is the same thing as what? Stress. That's Young modulus. FL over AE by mathematical derivation. Okay. Then another concept is work done in an elastic material or the elastic potential energy. Work done in an elastic material or energy stored in an elastic material. Okay, and that is elastic potential energy, which could be used to do work. For instance, when you use an elastic material like catapult to release a stone, you are converting the elastic potential energy stored in the catapult into the kinetic energy of the stone when it is released. That is stone in motion. Okay, so what is the formula for this work done? The formula is given by work equals to 1 over 2 Fe. That's the formula. So work done in elastic material equals to 1 over 2 Fe. Or, since F is equals to Ke, it can also be work equals to 1 over 2 Ke squared. So this is the formula. So for work done in an elastic material. Thank you so much for this, for paying attention to this class. So this is basic. Next time we shall go into calculations involving elasticity. I believe with this you have understood the key concepts in elasticity or elastic properties of what? Solid. We stated the Hooke's law, we explained and then discussed the graph, then we discussed the tensile stress and strain. Our stress is the ratio of the force to the cross-sectional area, while strain is the ratio of the extension to original length. That is it. You can see illustration. The original length is L1. You applied force and extended it. So the L2 is the final length when force is applied. So that is it. For more of these teachings or solutions in physics and mathematics, you can reach out to me through my phone number here. You can chat me on WhatsApp for online classes, preparation for JAMB, WAEC, GCE, NAFTEP, NECU, through my YouTube channel, through my WhatsApp. You can reach out to me so I can hold online classes for you through Skype, Zoom, Telegram. I remind